Yeah, 38 years. This is basically counting back to my diploma thesis, where I developed my first performance tools in 1987. I just realized by discussions this morning, I should have slightly made a slight modification to the title. It should be Memories of a Parallel Performance Engineer. I always was interested in how to optimize communication, synchronization, parallelism, and not so much the more node level single core performance things where the experts sitting here in Erlangen. So that we are kind of nicely match each other, with your experience and our experience on the other side. Okay, I basically made this talk historically. So people at least in the room should recognize the picture. So it's the Meanwhile Handler Tower, I think it's called in English. So it's the Institute for Informatics in Erlangen. And I've been there basically, I've been there 82, starting my computer science there, but working on parallel tools was with my diploma thesis in 87. And the context was at that time, there was a Sonderforschungsbereich 182, Multiprozessor and Netzwerk configuration, like multiprocessor network configurations. Went over 12 years in 4 times 3 phases, and I was part of it in the first 2 phases. For the people who are non-German, so Sonderforschungsbereich is like a large grant given to the university. I think in our case, it was over 30 PhD people working on different aspects from like operating system all the way up. And as I said, it's early 80s. And it was like really very early time for a university to think about parallelism, parallel computers, and so on. And I personally was part of Work Package C1, Messung, Modellierung und Bewertung von Multiprozessor-Rechnernetzen, like measurement, modeling, and evaluation of processes and networks. And there's a lot of parallel system development, so I encourage you to come here, and there's actually still, these machines are partially visible here, and you can see them. So ECBA, which was the first parallel scene already in the 60s or 70s? 70s. And then DIRMU and MEMSI in the 80s, early 90s or something, yeah. Another thing what you see is I, of course, for this talk, I took my old slides, and at that time we didn't have no PowerPoint, no laptops yet, so it was really like with overhead foils, and some of them actually, that you can see this where I try to explain is where Erlangen is to other people in Europe. They're really hand drawn and hand colored, but most of them are, we had at least a laser printer, and you could basically do the black and white printing on the slides and then just use like markers to do coloring. So what did we do at that time? So as we had already different systems we need to analyze, and when we want to look at different portions, at operating systems, at the program levels, at the application level. But ideally, when you monitor and evaluate these things, you want to not use different tools. You want to have one tool. So the idea was we want to do a monitoring and analysis system with what we called at that time object independent. Now we probably would say it more like portable or something with it, And the interesting thing, what we did at that point, and at that point we could do that because the systems were not too large yet, we did so-called hybrid monitoring. So nowadays, basically everything is done in software. You take your software, you put special instrumentation in, or with sampling, you stop the processor core and extract it, but everything is done in software. But here we did, to keep the overhead low, we called it hybrid monitoring. So the event definition by inserting instructions into the source code was still done in software, but that basically just triggered a signal to some hardware element, and then the recognition of that signal, the recording, the timestamping, the buffering was all done in hardware. So the instrumentation overhead was basically one instruction, like writing a value to like a store instruction. Yeah, you wrote a value to a specific address, and this was captured. And by looking at the different addresses and different values, you could store all kind of interesting information with this one thing. The problem, or yeah, the thing is now you have to have hardware to capture all that. But we had a Sonderforschungsbereich, we had money, and we built that. And this is the board we basically built at that time. And it's called Zählmonitor 4, Counting Monitor 4. So the numbers suggest there were also Zählmonitor 1, 2, 3, but it was even before my time. So I actually don't know much about these. And it was basically implemented as a board which you could plug in a standard IBM PC. On that board, you had a high resolution clock of 100 nanoseconds. You had a buffer of 32K events, each 96 bits, but the hardware was built that you could have bursts of 10,000 events per second. And the idea was basically, it was like organize a FIFO buffer while the information came in, some software running on the IBM PC emptied the buffer, so over time, basically could recording. And then we had a fixed board, and then there's this interface thing here. So depending on the hardware, we had like a standard 48-bit, how do you call it in English, Stecker? Connector. And then basically, depending where you want to plug into your system, you had kind of adapter cables with sometimes additional logic or not, depending how the interface were. And this way, you could reuse this board as much as possible. And when you had very specific targets, in the worst case, you had to build some specific adapter cables. And then it also had the idea, so if you want to just record like smaller values, one board could record 4 independent streams, but typically it was done like that, yeah, like if one board was not enough, you just like clicked another board in another board. And I think at that time we could plug in 4 into an IBM PC. And then if that was enough, you just got a second IBM PC. So you just was only limited by the number, like the money, yeah, how much you want to pay for all that system. But what I want to stress here, there was a cable going through all these boards, and there was a built-in time synchronization. So this 100 nanoseconds was across all these boards. And it also took kind of a delay into account. I remember doing a measurement over there in the Handler Tower, the Blue Tower at that time, and one board was in the 2nd floor, and then you had the cable out of a window to a 6th floor, and we measured kind of sending stuff from the 6th to the 7th floor with a distributed memory system with a 100 nanosecond delay. So I think it was amazing hardware at that time. So this was actually built by a colleague of mine, Richard Hoffmann. But he started at the same time when I started, and I was supposed to write the analysis software. Yeah, like he recorded the data, and I was supposed to analyze the data, make my graphics out of it. The problem is, at that time, Richard didn't even know what it looked like or something. Yeah, like now I know it, but it was after that when I was also supposed to finish. So how did you solve that? So my major in computer science was compiling systems with Professor Schneider, as some people know. So I like languages, parsing and lexing. And so basically I developed the system called Simple, and it was totally configurable. Every component had its own description language. Yeah, there was like a trace description language, a filter description language, again, diagram description language, and so on. So it was fully configurable. And this way, once our Zählmonitor hardware was finished, I just wrote the necessary description languages and I could basically plug it in. But meanwhile, I could analyze all kind of stuff. Yeah, there was a network analyzer who recorded packets. So packet is also like trace. Yeah, like each packet is an event record. And so I just described the layout of a packet. So I could analyze with my system a packet analyzer trace and so on. Yeah, and this is basically the whole system. Yeah, and but basically the most stuff I understood. So there was the base was this poet library, the problem-oriented event trace interface. And the idea is basically you have an event trace which has segments. Each segment is a list of records, and a record is a list of fields. And then you had basically functions which say, like, yeah, how many fields do I have? What type is it? What kind of content? Then you had functions to move backward and forward in the trace. And then once you said, I'm now on that record, you could extract information out of the fields. And it was like this generic interface. And then to make it yeah, nicely readable, is I came up with this trace description language, and you see a little example here on the right. You can later look at the slides. I don't go into details here, but I guess you understand issues. And over time, I made it work that I could describe like ASCII or representation, but also binary formats, and it worked out very nicely. And then based on that, yeah, so like the trace description, like I said, okay, there's a field called time, and then there's a field called event, which has these values or something. And then basically all the other stuff, you could basically reuse these names. Yeah, so basically, if the event is that, skip this record, or yeah, so basically, so this is how the whole thing kind of fit together. And so here's a language of a filter. We had tools for validation, yeah, like is the number of iterations start events as the same of the end. And when you went through and says yes or no, we had yeah, like basic statistics, which gave out your little boxes or statistics outputs. We had like looking for patterns in the events. We had a Gantt diagram generator, and it either again, this was, yeah, like late 80s, it would either print out a postscript you could print out, or it used this kind of line graphics in an ASCII terminal to make simple diagrams. Yeah. Yeah, we had even like an animator where you could basically say, okay, if this event happens, you could either create a graphical form or change the color or move it or something. That if this event happens, then we could basically things would move around and things like that. All kind of interesting little tools. Here's actually a list, which I think it's more interesting, is what kind of systems did we analyze? Yeah, and so there was this Dirmu, which was like one of these experimental parallel systems we had here, and then in the second column you see what kind of interface we used for hooking up to the system. Here was just a parallel port. Each processor node had like a parallel printer port, and we kind of connected to that. And then the instrumentation was by writing to this parallel port. Transputer, I don't know if some people had that. Here we developed, basically we took like the socket out, and then we had a thing, like let's see, a socket which you plugged in, and then the transputer is plugged in our socket. This way it gave us access to all the address lines and so on. And then basically just by writing in a specific address area, which was physically not there, and then basically in this range, basically the address encoded like an event, and then the value which was written to this location was stored as a value. And if it was into this special monitoring address range, it was filtered out, and the real transputer never saw it. And this way, again, with a store instruction, we could get values out. Suplenum, we used, there's a 7-segment display on the front, and we made it like the plugin, and when you wrote a 32-bit value, it was encoded in a sequence of 7-segment things, and then the adapter basically put it together again to a 32 cable. So it was kind of little trickery to get this working.
Question about the transputers. If you monitored actual addresses on the address bus, were those physical addresses? Did it have did it have virtual memory? or
No, I'm not so of a hardware guy, but as I understood it, so basically at that time you could already address like your 4 GB or 2 GB, but a real system only had a few hundred megabytes. So we just used basically the very end, which didn't exist, used this address range to write to that, and when we could use a whole address range for, as an encoding an event and the value, but because it was, but we filtered that out. So basically our interface never gave it to an underlying transputer. So when the software wrote to that, which doesn't exist, it never showed up and created a memory fault or anything like that. So it was very portable. We even sold it to IBM, Siemens, and some Chinese people, like the software and the hardware. So it was a very nice thing. So that was my first phase, basically here in Erlangen, and so basically I want to give this a little bit with the experience part. So what worked, what didn't. Yeah. So what worked extremely nicely was this hybrid instrumentation. Yeah, the overhead was minimal or basically not existing. It required some effort, but it compared what we have to do now, where basically as soon as you want to get some interesting value, you create overhead of easily 10, 20, 30%. With the hardware monitor which was developed was extremely sophisticated, highly advanced, that we even sold it. That was really good. Then I liked this idea of this very flexible trace analysis framework, and which could basically say, I can take data from all kind of inputs as long as it's something like a trace with like records with fields. And you just describe it and analyze it, and then all the tools was there. So it could be simulation outputs, could come from software tracing, hardware tracing, analyze log files, whatever. And of course, all kind of applications, it doesn't matter. What, like the negative part was, yeah, I mean, ZM4 was just too expensive for real large configurations. I don't even know how many boards we had. We had for sure 2 boards. It could be we had 4, but I think not more. But for the, yeah, typically you looked at 8 processor runs or 16 processor runs at that time. Yeah. And then this is where I'm basically most ashamed of. No, actually second ashamed. I say the most ashamed one comes later. I called this tool simple, but it was anything but simple. And I guess the only person who fully understood it was me. Yeah. So there was a binder like that with basically like 10 pages for the filter description language, 10 pages for that. And so what particularly happened is like for IBM. So they said, okay, this is our basic application. And I configured, say, okay, here's the standard like statistics output and so on. And I gave them my configuration files. And then they adapted it, yeah, like adding a new event or something. But the full thing was just too complex. And then what we found out later, especially the tool where it was with this automatic animation. Now suddenly, whatever, a packet was moved from here to here, but we know it was wrong. But didn't know, was the measurement wrong, the instrumentation wrong, or was just our description how to make the animation wrong? And so you had an additional level of things which could like, yeah, to debug and so on. But yeah. So, but it's always kind of yeah, like how flexible and how useful it is. It's always kind of this, you have to find the right compromise. Okay, that was the early years. Then after that, I got a postdoc position in the University of Oregon in a DARPA project. And the context there was, it was early 90s, so that was from 93 to 95. There were a lot of interested in parallel programming. And DARPA, like the defense portion of his ARPA research funding in the US, they developed all kinds of parallel language projects. And one I was involved in was called Parallel C++. It was basically a data parallel C++, but it's not the, yeah, it was C++ 92. C++ 92 was basically C with classes. Yeah, you had classes, object-oriented. It didn't have templates yet. It all came later. But for this very simple object-oriented C, basically we developed that. And it was basically two groups. The first was a group around Dennis Gannon. Some people might have heard his name. And he had a postdoc, Pete Beckman, who is is now in Argo and was at the things. And they built basically the PC compiler and runtime system to basically make PC++ run on all the systems. And then there was a subcontract to a person, Al Maloney, who just started, basically, it was his first year in Oregon, and he hired me as a postdoc, and we developed a performance tool for this parallel C++. And I named it Tau. Yeah, and so basically here's some old slides about PC++. Yeah, you have a class, and when you define an object of it, then you can call a method on that object. Yeah, this is a normal object-oriented way. And what we basically added was what we called collections, and then it was vector, list, and I forgot the third one. We had like three different. Now we have kind of like in the standard library, kind of these templates, but we had it kind of hard-coded. And so we could say, I want to have a vector of this object. And then if you can call a method on this collection, it was called on every element of his collection in parallel. And of course, there was ways of distributing these over different nodes and processes. That was a very simple version. And then there was now you would use LLVM, I think, to implement it. And at that time, there was something called Sage++. It was other compiler, C++ toolkit to analyze code and restructure it and so on.
There would have to be a very complex runtime system below it, because you need agents on the nodes, you need to distribute data.
And you want to have it running on every, and in the mid-90s, and I show you a list, we had like from here to here, like, there's another story, but I come to that in a second. Yeah, and I said, and I basically implemented the tool, and this is how I usually start. First, I have to have a name for the tool and a logo. And so I started with tools are us. Tau was a simple thing. But then after a while, like Alan pointed out, because, yeah, you know, it's a pun after this Toys R Us, people could think the tool is a toy or something. So, but the name was established, so we changed it to tuning and analysis utilities. And so I invented, and this is basically what I did. I invented with this Tau logo with in the early days it had these kind of Atom things, and I came up with a tame tuning analysis utilities, which is my thing. And when the team we had there was like multiple people, and because the Ducks is the football team of the University of Oregon, we called ourselves the Paraducks. And we took the logo from, and they had as a mascot the Donald Duck from Disney. So I stole basically their kind of logo and replaced the football with turning laptop. Like just a side thing. So, and that again was the environment. There was on the compiler on the left side. And then basically with Sage++, which was not only basically did the compilation and the generation of a parallel code, but also exported a lot of statistical information, which I can use within the tool. Yeah, so the tools basically had static information from a compiler and then all the runtime information. And then the idea was I have little tools, and each tool did one thing. Yeah, like the fancy is a file and class display. It was a file and class browser. And when the tall graph display was cagey. Yeah, and then so it was always like a positive adjective. So if someone said, "What is Tau?" I could say, "Yeah, it's cozy, fancy, cagey, classy." So it was like kind of a running joke, and we had lots of them in there. But I have to stress, it has very little to do with the Tau now. Yeah, it's just the name, the logo, and some basic ideas how things are structured. But at that time, it was only working for this parallel C++, but nothing else. What I implemented with little tools, it was implemented tickle decay, and was easy and nice. And the idea was, I mean, as I said, it was before, I think 93 was the first invention of the internet. But like with ideas with hyperlinks and clicking on something, which just came. So this was the first idea where I said, okay, I want a tool and I see something interesting, I click on it, and like a hyperlink, it gets me to the like more details about this object. And that was one idea. So I had these kind of hyperlinks. And the other one, if I had like 5 or 6 of the tools available, and I click on, say, a specific function, and it clicks, all the other open windows also have information about that function. So when they all basically zoomed in or highlighted that specific function, this is what I call global hyperlinks. And so you could click, and then basically everything synchronized itself. And I thought that was a very nice idea. Yeah, so basically you had your basic profile display, and you say, okay, I'm interested in this yellow function. You clicked on it, then basically from the profile display, a window came up which showed you the performance on each of the different processes. But if you had also the source code browser and the call graph browser out, it also highlighted it with the functions at the same time. Or you could look in the call graph browser, and it showed you again, if it was profile information, it showed you profile information. So it was working in both directions. And again, we had all kind of, this was the main interface where you could basically start the compilation, and the execution, like the launching, and then there was a little, say, now launch with monitoring and what kind of to record. So it was, we tried to have like a little graphical environment there. There was source code browser, call graph browser, class hierarchies. This was the profiler, and when you look at the output from, like the text output from the tau profile tool, paraprof or something, it looks a little bit the same. I think it still has the same columns, and so there's some stuff survived, but yeah. And here some of that, I said, this is for PC++, and it had basically the basically this is for each process, and then basically each color is for one function. So you have basically the histogram kind of made in one line, and then over the different processes. And then you had, this was show you all the performance from the code paces, and then you had a window for the collections. And then later the Tau people basically made it more general. Basically this collection stuff went away, and the rest is left over. And so some of the stuff you can, like this display, like down here, I think you could still have, it looks a little bit like current Tau. I mean, it has more buttons now and more right context things, but it's this, the basis was from there. We also had like a very simple event trace visualizer, self-written, but we already had converters either to Upshot or Tableau using other tools. We had a modeling where you make measurements, and when you try to kind of what Dimemas from Barcelona now does is say, okay, if it's kind of continuous like that, what we basically if you have a twice as large system, how would it develop? And you would get some extrapolation. Yeah, and this is kind of the list of systems Perl C++ worked on. As I said, at that time, it was kind of an explosion. It was the beginning of a parallelism of clusters, and all kind of companies try to come up with a system and build them. So it was running on the KSR, a cache-only machine 1 and 2, on the sequence symmetry, on SGI, Perl machines, on the convex, on the BB Butterfly. But it was all shared memory, and then on distributed, we had the thinking machine CM5, Intel Paragon, IBM SP1 and 2, the Creativity and 3E, Mako, and workstation clusters in Unix. And I would say half of the time in my project, we try to get, coming back to your questions a while ago, is making this runtime system working on all these different machines. And then after a while, we even found out, hey, yeah, like there was another one on a parallel, I forgot the name, a parallel Fortran compiler project. There was another one, CC++, concurrency++. And so we all got together and we talked about ports, the portable runtime system. So we write one parallel portal run system for all the language, for one and for all, and then basically everyone can use it. So and we never got it to a point, but some people, Ian Foster and Steve Tücker, took the original port stuff and made Globus out of it. Globus is a name. Globus is like a toolkit, and this has its origin out of this creating a portal runtime system for these parallel languages at that time. Yeah. The other thing I'm also kind of proud of here is now we would call it portable performance or performance portable. Yeah. So you could run on all these different systems, and the performance was always the same. It was horribly bad everywhere, but it was kind of consistent. But it was portable. Yeah. And then this is it was in the last year, was still there. We had connections with the Portland Compiler Group, which is also in Oregon, which developed later into, I don't know, now it's basically the NVIDIA compiler. And they had worked on an HPF, high performance Fortran compiler with an interface. And he said, oh, we have these tools, and can we kind of have a little massage kind of made? So we basically make the file browser, the call graph browser, and the profile display working for that. And they say, oh, now we have kind of a tool now also working for Fortran. And then when I left, said, okay, now why not also for C++? And so after me, basically, people basically made it, basically Tau working for this, Tau working for that. And this is still around. Yeah. So, but it has its origin basically in this core stuff I developed in 93 to 95. Okay. So what's worked here? We had a very early, fully featured parallel programming environment. And it was kind of easy to use. I mean, you put, and then you had a build, run, analyze in the graphical interface for 95. That was kind of good. We had these kind of global features with these hyperlink tools. And even as that it was originally built for PC++, it was flexible enough you could like target other languages. And so this is kind of how it developed into what it's now. But I have to say, basically, this was basically 95 when I left. All the real interesting stuff was done after me. Yeah, so I said, the only thing I can claim is the logo and the name. And I don't know who of you tried to install Tau once. And it has this horrible configure system. This is a handwritten script with configures that is also my invention. I put it here undecided because I think it still works. Very simple, was very simple. And especially if something goes wrong, you can easily debug what goes wrong. But other people said it's the worst configuration system ever. So yeah, I'm responsible for that one.
Make us any better.
Yeah. No, but this is just a hack of SED scripts and shell scripts. And the basic idea is simple, but make it really fully work, it's required a lot of hacking. So what didn't work so good is especially when we want to get more and more into like not just parallel C++, but normal C++, especially later C++. C++ language is so complex. So without having access to the compiler, which at some point was, now with LLVM is easier, but at some point there was nothing like LLVM. Supporting it was really hard. And we tried in extending with H++, and so we licensed even the EDG parser. I don't know, some people might know. And also it's really, Tau is really good in profiling, but it has its weak point in tracing. So it can generate a trace, but doesn't have any good trace tools. It leaves it to Vampir and other tools. Okay, so that was basically the, I mean, still last century, but it's, yeah, postdoc years. And then I came to Jülich, Jülich Supercomputing Center. It's part of Forschungszentrum Jülich or Research Center Jülich, which is basically a large national lab. 7,500 people working on all. It's like a campus, like here in the northern part, in the technical faculty. So 40 institutes, and it started out as like the place I'm working as the Central Institute for Applied Mathematics. So these were basically mathematical people who helped the other scientists on the campus doing their calculations and come up with better methods. And then I think in 1962, someone bought an IBM mainframe, and then we slowly developed into a compute center. 87, we claim the first national center, but Stuttgart also claims they were the first, but we were one of the two first national centers. We were the first praise center supporting Europe and so on. And then later it was renamed to the Jülich Supercomputing Center, especially once we had like these large computers. Jülich Supercomputing Center has something like 350 people now. Yeah, it's quite a site. And originally, I was only there, basically, they gave me a job after coming back from US, because I kind of, in these 3 years, there was not real internet yet. So I had a hard time finding a job back in Germany when I came back from US. So they hired me, said, for 2 years. So then, and then from Jülich, I could basically go somewhere else and find a real job, but I never left. So I'm still there. So it's a very long second phase. And so it was like I came there in 96, and I was there together with, in the beginning, with Michael Bernd, who is now professor in the Technical University of Munich. And we both said, oh, all these tools are nice, but they're so complicated to use. But a performance analyst and expert knows a lot. Can we somehow encode this information to a tool? And then the tool doesn't say, here's the numbers and the histograms, but says, this is wrong, fix it, or that. And we call that automatic performance analysis. And this was the idea. We didn't know how to do it. That was the idea we want to work on the next years. And when we founded first with other people in Europe, we got some money. We called Apart. It was kind of a working group on like discussing these issues. And then later in 2006, together with Felix Wolf, who was originally a PhD student of mine, now also a professor, we founded with VIHPS, the Helmholtz Virtual Institute on High Productivity Supercomputing, which is a loose collection, meanwhile, of many people working on tools, debugging and performance tools. Yeah, and so originally we implemented, like the first thing we implemented was KOJAK. So the idea was, I don't know, it's probably, this shows how old I am. Typically, not many people in the room remember KOJAK, the police detective from San Francisco. So there was this guy who had no hair and had a lolly in his mouth or something. And the idea was basically, like KOJAK, basically you give it your program, and like the detective, it goes after the bugs and tells you. And at that time, basically, I mean, it was a parallel, but it was still kind of parallel performance, but the analyzer who basically did the automatic analysis was sequential. It was just a Python script at that time. That worked well the first, I think, I don't know, 5 or 6 years, so 2003, 4, 5. And we used it in training. like online, like in training sessions and tutorials. But at some point, like just the analyzer run took an hour. And then so you cannot make like a half-day tutorial if like 1 hour, like you have to wait for the output. And then the idea was, hey, like, can we do that in parallel? And this was the idea behind Scalasca, the scalable analysis of large-scale applications. It's basically the same thing what we did in KOJAK, just in parallel. Okay, so what does this thing do? And this is, and I marked here kind of where the slide has come from, because at that time I could recover. And at that point we had PowerPoint already. I think me, Michael Bernd, we were the first people in Jülich who had a laptop for PowerPoint in 1999. It was like 3 kilo. So the idea was basically, yeah, like, so you typically, yeah, you have some monitoring system, you define your metrics, you collect that, and you get like this huge portion of data. Then you have some simple analysis like calculating derived metrics and things like that, which makes it basically like even larger data, yeah, and then yeah, and then on top of that, you have all these thousands of tools and timelines and histograms and bar charts and yeah, and but then there's the poor user, yeah, and yeah, he gets crushed by that. So I had to remove that because some people found it a little bit, I cannot crush users, so I had to come up with different slides. But I thought, like, now in this like historical look back, it's nice to look at some of the slides from back there.
Very early 2000s.
Yeah, and then basically, yeah, and the solution, of course, is, yeah, like you have your huge amount of data, and then you have your expert automatic analyzer, and it reduces it basically all the things you need to know, which is just like this little thing, yeah, and yeah, and you have one tool which tells you basically, this is the problem here in the source code, here in the machine, and then the user can easily juggle that. Yeah, so that was the idea. Yeah, and it's clear this is for standard cases. Yeah, the typical things what especially beginners run into for the normal users. And if you have like really like sophisticated users and run into specific problems, a performance analyst can use this tool to say, okay, does this, what the problem the sophisticated user had, is it a simple thing and my tool finds it? But if not, I can basically say, okay, it's not that. And I can look in other things and I can use it as a starting point for the other stuff. Yeah, because I know basically already what portion of that I can kind of ignore. Yeah, so that was the idea. Yeah, and we started with MPI. That was, as I said, like early 2000. And the idea was, okay, we know what are the typical performance issues when you do parallel programming with MPI. Yeah, and one thing is, you see basically here, everyone is working on a routine called velo, but process 7 is done earlier. And so when we exchange messages at the end, he wants to get a message from another processor, but it takes quite a while because the other are still calculating. So the send of a message comes too late, and he's kind of wasting at least this portion from the beginning of a receive until the send was recorded. And this is what we call the late senders, was kind of our running example we use for, I don't know, 20 years, but it's very visualized and easy, and people understand it. And basically what Expert and the latest Scalasca did is we come up with a collection like these, like a larger collection, for each of what basically said, what is the the event configuration, which basically is this problem? And for each of them, we say, this is the time you wasted for this problem. And when we just go through, just in quote marks, we go through, look for these patterns. Every time we find one, we say, okay, we found problem late sender 1, and we wasted so much. And then at the end, we can say, you had 10,000 late senders and you wasted 10% of your time because of that. and you had whatever 1 million of these problems, but you only wasted 5%. So we basically know what things occurred, what the reasons for these are, and the impact on the execution. And we also know where in the code. So you get that it could be like whatever 10,000 late senders, but like 5,000 here and 3,000 there and 2,000 there. Yeah, and that's basically what KOJAK and Scalasca does. Yeah, and so here's some others. Like up here is kind of like this, what I just explained, the late sender. You could have also with blocking communication, like when the receiver comes too late, when you're wasting time at the sender. The usual like barrier or synchronizing all to all, where yeah, like the last one, basically all others are waiting for the last one and they're wasting in multiple places. So this is the simple stuff, but you can go on. Yeah, so like when you look here, the late sender on the upper left, it's basically the same down here. So if we find a late sender, we look, is there another message also to me, like the lower part, but it was sent earlier. So if like this process down here would receive that one and that one, it would go faster. Yeah. So we say it's a late sender because of wrong order, or a late sender because of wrong tag. You look for a wrong tag. And so you can build more and more complicated things. And the more complicated the pattern is, the more details it gives you basically what was wrong. And so meanwhile, I mean, we have, I don't know, 12 or 15 MPI ones, stuff for OpenMP, and we're looking into how to make it work on GPUs and stuff like that. And then how do you show that? And basically, you get profile data and you have metrics for your code and on the system. So it's with 3 panes, 3 dimensions. But you realize very quickly that each of these dimensions is kind of hierarchical. I start on the right. So the system is out of nodes. On the nodes, we have processes. The processes have threads. And now we have streams on GPUs. Yeah. And so you have it's kind of this hierarchy. Source code hierarchy is also clear. Yeah. A function calls another function, calls another function. And also on the left side, yeah, you say, okay, time. And when the time metrics opens up in compute time, MPI time, OpenMP time. MPI time splits into communication time, synchronization time, file IO time. Again, and you can basically open and close. And so the idea is basically we show this information because we have all this information of all metrics on every place of every call path and on every thread. And by navigating this 3-dimensional cube, you basically select which portions you see, and you see either planes or lines in it. And then we have this thing here on the right, basically. So if it's closed, yeah, so basically, so I spend 100% in main. When I click on the left, I open up, I see the next level, which means, okay, now 30% is spent in foo, 60 in bar, which means 10 is like left in main itself. Yeah. And so this the number here changes if it's kind of, is it exclusive or inclusive? Yeah, when you open it up. And so basically this is how a tool looks like. This is with 3 panes. Here are the metrics. Here's the call tree and the system tree. And you have basically 2 operations. Yeah, you can open, like basically go deeper in the hierarchy by clicking on the plus minus. And so you choose the level of detail in each of these dimensions. And if I select something on the left, on the left panel, the value of it shows me how this is distributed in the next level. So I select the time metric here. Then basically I see basically how is whatever 1,500 seconds are distributed on the different functions in the call tree. And when I select a specific function, then I see how the time spent on that call path is distributed over different processes and nodes. And by open and closing kind of on a system tree, I can see how is this time distributed over the nodes, over the processes, over the threads. And yeah, and the same thing here. Yeah, how is MPI time distributed, or how is MPI communication time, or point-to-point communication time? I can select the detail, and I always see the distribution on the left side. And this simple three-pane model allows you to browse all that once you understood how it's working. Yeah, and this is the thing I want to basically come to, and this is my last message. So we developed this interface 2001, 24 years ago. And if you download Scalasca now, it more or less looks the same. It has these three panes, the same operation. It has now extra context menus and other buttons, but it's basically the same. So many people come to us, what did you do in the 24 years? We did a lot, but it's all hidden, yeah, in the measurement portion and the analysis and so on. Yeah. Okay, and then basically what I have here, so as it's 2003, yeah, and it's just basically said what I explained. Here it's from 2007. We had a first blue GNL with 8,000 processors. And then this list of the list of processes, it got very long. But when the blue gene had this three-dimensional torus, and we said, oh, why not basically make an extra display where because we know the mapping of the processes onto this three-dimensional torus, how basically, yeah, we show basically the three-dimensional torus. And so if a machine had a nice how you say that? A nice three-dimensional model of how it, like a mesh or torus, we showed that. But we also record Cartesian coordinates from MPI. So if you have Cartesian coordinates, we also can show how the data is distributed over your communicator. Yeah, and if it can be also two-dimensional, like the standard one is processes and threads. Yeah, process one way and threads and the other. So we added that 2007. Here, application topologies. This was a measurement on one of a sea ice model. I think this was actually WRF. So if an application had a topology, we also added an interface to record that, and then you could see the performance metrics on the application area.
There's a very hot column across, Russia, Turkey, Northern Africa.
I don't know where that came from. I can explain the next. So this was, I think, it was WRF, but we had another one. Yeah, this is also kind of it was CSM, the Community Earth System Model, the sea ice module, running on 4,000 cores, and it basically they had quite some late center. I'm gonna get my classes out, sorry. Yeah, it's basically the MPI weight all inside the ice boundary calculation and so on. Yeah? And you can see the weighting in the equator region is kind of quite high. This is kind of natural because there's very little ice. Yeah, so okay. But at that point, people said, yeah, wait a minute. The problem is not that these things are waiting. The problem is that the stuff which happens before is not equally nice balanced. So the weighting is not the problem, but the problem is actually the imbalance somewhere before it. Most of the time it's just in front of a barrier, but it can be 3 or 4 phases before, and it just gets moves through. Yeah, and then basically here's another one. Oh, I don't have that. Oh, so yeah. And then what we implemented is kind of a backward search. So every time we find a pattern and it has waiting time, we look for the imbalance which causes it comes from. So we can tell you actually this waiting is coming from here and how much the imbalance is where. And it was much useful. I didn't have the slides here. Yeah. Then we got a blue gene P, which had 300,000 processors. It was 2010. And just to give you some idea, yeah, so it was a benchmark sweep 3D, ran for 10 minutes. The actual analysis of the trace data was 11 seconds. but the first application around, when we had to dump all the traces to disk, took 4 minutes. I mean, it's a high-performance computer. When you start our trace analyzer in the same job, he reads it again. Oh, it's actually read and write 4 minutes. Yeah. And then the actual analysis was 11 seconds. Yeah. And it was like 7.6 terabyte trace data and 510 billion events, 2010. So this is how scalable Scalasca is. But that was actually not like our world record, if you want to call that, was on the Blue Gene Q, where we had something I forgot, roughly 500 million cores, but each core was 4-way SMT. So we could, so first, like it was the first one, 2013, we broke the 1 million thread. And when our largest measurement ever, I don't have, it comes later, okay, here, was 16 then, basically, where we did basically really every SMT thread, and we would 1.8 million threads where we measured. And it's still, okay, as you do the analysis, you still get all the data and have it. This is how scalable it is. As far as I know, no one told me has ever done a larger measurement. What I don't know is what some physics explosion, atomic bomb simulation people inside the hidden sectors in US are doing in their labs. But on the open sector, like the Tau people said, they did something with 700,000, HPC toolkit also in 500,000. No one basically had such a case like that. Yeah. I see that the time is running out. So meanwhile, we implemented all kind of our interesting plugins to show phase diagrams and other stuff. But basically, it's the same idea. Yeah, you look for this pattern, show them in the 3-dimensional tree, and then just like make it work on all kind of machines for every graphics like we have now: CUDA, ROCm, Cocos, OpenMP Target, OpenAC, like all this stuff, and yeah. I also found that funny. So, I mean, you can read yourself, you made it when large companies copy your stuff. So at some point, just by accident, I came about an Intel manual, and they introduced the Intel Trace Analyzer Collector Performance Assistant, and it had things like late broadcast, late sender, weighted barrier. And so we copied this analysis, and we even copied our names. I mean, we could have, which is actually nice because so we kind of established the patterns, but we never mentioned anywhere in this document where we got the idea from. And this original document doesn't exist anymore. But when you look at the blue line, this is the latest user manual. There's still some slides about this performance assistant. So it's still in the Intel tool. Okay. It was a student, basically, when he finished his diploma thesis, he made this late receiver cake. And we were all kind of a little bit disappointed because it didn't make a late sender cake, which was our main thing. But yeah. Okay. So assessment about this. Scalasca, we worked on it, as I said, for over almost 25 years now. It's installed in many sites. Many people use it daily, like the Pop COE is using it, other people. And this is, I'm really proud of. We have a user interface is consistent for 24 years. So people, once can know our tool, they can still use it, has more features, but the basic idea is the same. And we also got some support by vendors. Intel paid us to make adaptations for the Intel mic, no longer existing, but an AMD is now paying us for ROCm support, and even Siemens paid us once for Windows port. And then, of course, lots of stuff happened. Constant bug fixing, constant scaling improvements, and then now, I mean, there's all this, especially with GPU support, is like taking at least 2 people or something, just working on making it all work for the different GPU models. But also, new MPI coming out, new OpenMP coming out, the Fortran 2008 interface from MPI, blah, blah. We're constantly busy. There's 10 people in my team just working on Scopy and Scalasca. So when you just say that for say 20 years, so this is like 200 man years of work. And yeah, so that's basically it's my personal history, the tools I worked on. There's probably other stuff, but it's I would take another half hour. And I thought I could close in what at this moment I think is currently not working. Yeah, so if you have students who look out for like interesting topics, yeah, what kind of things could they work on? So I think, and you might disagree with me here, but I think memory and vectorization analysis is hard. Yeah, because you basically get some indirect information how well it's working from the hardware counters. This is very processor specific, and it's really hard to make it work. So if you're Intel and in VTune, you can make it, but as a Portal 2 developer, it's basically hard. But even that, it's very hard to make it work. Say, yeah, like here in this phase of a code, I have a vectorization issue, but or a memory like cache problem. But which of the data structures is it? Is it array A, B, or C? There's methods to do that with sampling, but this is, I think, yeah, hard for people. But the biggest thing for me is this trend towards this task-based asynchronous program models. You know, like you have like GPU have kernels. Other people just also with CPU will write tasks and graphs, and they work best if all these executions are really asynchronous. Like if I launch it and wait for it, it's still synchronous. But if you really so on. And when you have a problem with a little overhead instrument measurements, the execution of these asynchronous tasks can quickly change. And now our nice model, which we're using for 30 years, yeah, I see a problem, I instrument it, I analyze it, say, oh, here's the problem, I rerun it with, it doesn't work anymore because if it's run 10% faster, is it coming because of the phase of the moon or the temperature of in the machine room, the asynchronous execution was just faster, or was it because, yeah, like I have these cases where you insert instrumentation, the code ran faster just by inserting instrumentation, and things. Yeah, I mean you know that, and so all these offline tools will fail at some point, but it's even. So timeline, you can see nicely with asynchronous executions, but it only works for like a node in a specific time frame. It's like longer executions, the whole cluster. You can browse along and zoom in with timelines, but it's hard to find. And what's missing here is how do I show the performance in a nice, understandable way for these asynchronous execution models. But even Cube fails here because like in the middle, when you open and close, this is basically, okay, like the time spent in the children of that node is asynchronous. Yeah, so that if I have a kernel, like with open and closing, I follow the large number, it doesn't work anymore. So for 10 years, I push my people saying, how can we change Cube to make it work? And we don't have a real. Yeah, so we still, you get it, you see all the kernels, but then basically for each kernel graph, we have a separate thing, but you don't see the big picture anymore. So that's a really big problem, and I don't know how, yeah, but how people to HPC tool, no one has an idea how to do it here. Then we see the trend to really modern programming language, Python, C++, yeah, how to instrument template-based frameworks. We have all these inline methods, which you basically, yeah, if you instrument, you get too much overhead. If you're not instrumenting, you don't see them. And then Python, yeah, with all these modules in and getting all in one tool. Performance assessment, data analytics codes, performance assessment workflows. And then, of course, yeah, how to use AI methods for performance analysis. I don't know. So there's lots of things open you can work on, even after this like long thing. So that basically was a very quick rush. It still went over 1 hour. I'm sorry. Of 30 ideas of working on performance tools. Thank you.
a lot. Are there any questions or comments in the room, in the Zoom? Just put it in the chat or raise your hand. You can also unmute yourself. We can hear you over the room speakers. Yeah.
Actually, one question. I mean, you already mentioned on your last point, AI. Do you think it helps us with performance analysis or makes it harder because everything is just a black box and you don't even understand why something is happening?
There's two dimensions to it. I think your question goes more, I'm not sure. Is it more analysis of AI codes and frameworks?
Using AI for analysis of classical.
Because that's, people typically use a framework and we are not interested in, like we basically want Google to analyze the TensorFlow or whatever, and we don't care about. On our case, so the thing is, I'm not a big AI expert, so I'll probably say something stupid here. But my feeling is you have to have some labeled data, which you can train your model on. And once we would have that, we probably could do that. So if I would basically, all the performance, my assessments my team did, we had kind of written down and all the information and use that as a training. But it worked, but no one did that. Everyone did a training, used it, and then never wrote down this analysis in the data or something. And how unsupervised learning is helping here. Perhaps on, we started already basically, like as we have these topological display. So they say, like, if you have these diagram on the left side with like processes and threads, you can see patterns in here. Can we kind of train it to see specific things? But again, we still have to say what is bad, what is good, and somehow, so we perhaps I'm not, as I said, AI expert enough. So I see the potential, but currently I'm a little bit I don't know. And talking to my colleagues in the AI groups who also working on how to use AI for their science, said it's totally unclear currently. It will be useful, but will it be useful for all disciplines or just a few disciplines? Do you use one large foundation model which you can use for all of science, or do you have to have a model for whatever, astrophysics, for whatever, and so on. There's lots of open questions, and people need to think about all the data they have. How do they encode them? Because once you have a good model of your data, then you probably can apply the AI methods on them. But before you don't have an idea what your data is and how it's structured, what information is in there, you don't need to start.
I just want to add on top of that. So I've visited Lincoln this summer and talked with Jens regarding and he has the idea of kind of augmenting the XRP method by looking to the traces and see if it's possible for us to extrapolate the trace from a few ranks to, let's say, 100 or even 1,000 of ranks. But the main issue is it's not even possible to get, let's say, publicly available data sets. I emailed recent people regarding if they can share their own data sets, but they say no because they have some sort of agreement with their clients, so they are not able to share it. And I also asked to win people for this, but they also said no, we cannot share it. So I guess even the data source is a problem for now. Just like it's not feasible for.
A very good comment. I mean, you saw on the numbers what we have. So for a few, like for the sea ice model thing, where I can make a nice story, I have silver traces around, but I don't have all these other thousands of things. It would be terabytes of data, and who pays for the storage and everything. So most of them we threw them away. We kept the like the three-dimensional output, but the actual traces we threw away. But we probably would need for the training.
One question about the development of programming languages, programming methods, programming models, especially in parallel computing. So I have the impression over the last 10, 15 years that things are progressing faster and faster. So the standards are evolving faster than they did 30 years ago. So we have new C++ standards every 3 years. We have updates to OpenMP more frequently than 20 years ago. And you have to keep up with that if you want to develop tools that are compatible with all the options that open up. Do you also observe that?
Based phases. I remember in the 90s, yeah, suddenly we're like within 5 years, 20 different systems came up. And when, again, it was like this, you don't know, like which machine should I work? Everyone had slightly different. I mean, this prompted basically the invention of MPI because everyone had a different message passing library. And so but then there was a slower phase, like once you had MPI and OpenMP, and then at least for 10, 15 years, it was kind of stable. But with graphics cards in the interest through AI and other stuff, and the energy efficiency they give you, and you going back to these vendor locked models or different ones and not really compatible, and then people try to do something like MPI, look at Cocos or Russia or whatever, but you don't have one, but you have 10 of these levels. And so currently we have this kind of very rapidly increasing things. And I agree with you. And in addition, in order to make MPI and OpenMP work better with graphics card, because you need all three of it, they also develop again. So after almost 10 years of silence, suddenly there's like as an MPI coming out every 2 or 3 years, OpenMP coming out every 1 or 2 years. And with major new things, yeah. I probably could have 20 people in my team and we would be still busy.
Right.
But yeah, but this way it never gets boring. And I mean, when you see it, I mean, I'm working on performance analysis of parallel systems. It's like a very narrow, small thing. But I never ran out of work or ideas or something. And it continues like that. Yeah.
It's a small thing, but with a high impact on the resource you
Yeah.
use. I mean, you can easily burn thousands of 10,000s of euros in a day if you just do something wrong.
And 10 years ago, actually, on a public conference, I gave a talk like that and said, yeah, I mean, in the end, if someone would build a really easy to use parallel system with an easy to use programming, yeah, people would automatically just write efficient code, and my job, I would be out of job. Yeah, so I said, I basically, yeah, like take me out of my job. Yeah, come up with a system. 10 years later, I'm still here. Yeah, and so